All right, let's get into it. Today, we're becoming detectives and tackling one of the trickiest subjects in calculus, multivariable limits. If you've ever felt that jump from single variable to multivariable calc is like going from a quiet country road to a crazy 8-lane superhighway, you are not alone. But don't worry, we're about to crack this thing wide open. Okay, so let's just visualize this for a second. In Calc 1, finding a limit was, pretty chill. You're on a line and you just have to check two directions, right? You come in from the left, you come in from the right. If they're heading to the same spot, boom, you got your limit. But in 3D, whoa. Now our point is just floating out there in space, and we can approach it from literally anywhere. From above, below, spiraling in. There are infinite ways to get there. And that, right there, is the central mystery. If a limit only exists when it's the exact same value along every single path, how on earth can we check an infinite number of them? It sounds completely impossible, doesn't it? Well, turns out that's where our number one investigative tool comes into play. Let me introduce you to the two-path test. Honestly, this is the most powerful technique for any limit detective trying to prove that a limit does not exist. It's clean, it's super efficient, and it is absolutely going to be your new best friend. The logic here is just so simple and elegant. We don't have to check a million paths, we just need to find just two witnesses or paths that tell different stories. Think about it. If path A says the limit is 5 and path B says the limit is 10, well, their stories don't match up. And that contradiction, that's all the proof we need. So here's our game plan. It's super straightforward. First, you pick an easy path, something simple like the x-axis, and you figure out the limit. Then, you pick another simple path like the y-axis, and you find its limit. If those two results are different, you're done. Case closed. The limit does not exist. Of course, not every case is some grand mystery. Sometimes, the answer is just sitting there right in front of you. And these are what I like to call the open and shut cases. They really don't require a full-blown investigation. So if you're dealing with a nice continuous function, like a polynomial or sine or cosine, a lot of the time you can just plug the point directly into the function, no drama, no mystery solved. And if you run into that classic 0 over 0 situation, sometimes all you need is a little bit of algebra. Factor things out, cancel some terms, and the answer just reveals itself. So always check for these easy wins first. All right, time to open our first real case file. This is a classic, the kind of problem you're going to see all the time, and we're going to solve it with our good old two-path test, just by interviewing our two most reliable witnesses, the x-axis and the y-axis. Here is our suspect. We need to know what's happening to this function as we get super close to the origin, to 0, 0. Now, if we try to just plug in 0, 0, we get 0 over 0. So direct substitution is out. It is time to investigate some paths. Let's talk to our first witness, the x-axis. Now, along this path, the y value is always 0, right? So we just substitute y equals 0 into our function. And what happens? We get x squared over x squared, which just simplifies to 1. So along this path, the limit is 1. Okay, let's file that away. Now for witness number 2, the y-axis. Here, the x value is always 0. So we substitute x equals 0 into the function, and we get negative y squared over positive y squared. That simplifies to negative 1. So along this path, the function is heading towards a limit of negative 1. And there we have it. One witness tells us the limit is 1. The other says it's negative 1. Their stories are completely different. They contradict each other. So there is no way the overall limit can exist. Case closed. Okay, our next case file, it's a bit more of a challenge. Our suspect function here is a lot more clever, and the first bits of evidence can actually be really misleading. This is the case of the deceptive witness. So, a huge word of warning to all you detectives out there. Sometimes you'll check the x-axis and the y-axis, and you'll get the same answer for both. Maybe you get 0 for both paths, and it is so tempting to just stop there and say, aha, the limit must be 0. But that can be a trap. A really clever function can be designed to fool you along those simple straight-line paths. So take a look at this function. I'll give you a little spoiler. If you check the path along the x-axis, where y equals 0, and the path along the y-axis, where x equals 0, you're going to find that the limit is 0 along both of them. It looks like the case is solved, doesn't it? But a good detective always knows to dig a little deeper. When the straight lines agree, we've got to get more creative. We need to look for clues inside the function itself. See the denominator? We've got an x squared and a y to the fourth. That relationship between the powers is our clue. It's basically screaming at us to test a path that connects x to y squared, something like a parabola, x equals my squared. This path curves into the origin, giving us a whole new angle of attack. So, we substitute x equals my squared into our function. It looks a little messy at first, but after you do some algebra, the y to the fourth terms all cancel out. And, aha! Look what we're left with. The limit isn't just a single number. The result is m divided by m squared plus 1. And this is the smoking gun. The value of our limit depends entirely on m. It changes depending on which specific parabola we chose to write in on. So if we pick the parabola x equals y squared, where m is 1, the limit is 1/2. But if we pick m as 0, that's just our old friend the y-axis, and the limit is 0. And there it is. We've found two different paths, a parabola and a straight line, that give two completely different limits, 1/2 and 0. The stories will never match. This deceptive function has been exposed, and this case is closed. The limit does not exist. So far, we've basically been prosecutors, right? We've gotten really good at proving that limits don't exist. But what if we're on the defense team? How in the world do you prove that a limit actually does exist? This is the final, and definitely the most advanced part of our whole investigation. Remember the big problem? To prove existence, you have to show the limit is the same along all those infinite paths. And our trusty two-path test can't do that. It's a tool for finding contradictions, not for proving that everyone agrees. We need a whole new tool for this job. The master technique here, the big guns, is to switch to polar coordinates. This lets us think about any point in terms of its distance from the origin, which we call r, and its angle, theta. Now, approaching the origin from any path simply means that the distance r is approaching 0. So our goal becomes to show that the function's value gets to the same number as r goes to 0, no matter what the angle theta is. If we can prove that the angle doesn't matter in the end, we've covered all our bases at once. This usually means we need to pull out another tool, like the squeeze theorem, to kind of trap the function and prove its final value. For example, if we investigate a function like this one, x cubed plus y cubed over x squared plus y squared, using polar coordinates shows us something pretty amazing. After you convert it, you can actually prove that as our distance r goes to 0, the entire expression gets squeezed down to a single value. And it doesn't matter what the angle is. And that value is our final verdict. This limit does exist, and it's equal to 0. So there you have it. You've got the key techniques for limit detection. You know how to spot the easy cases, you can use the two-path test to expose those contradictions, and you even know about the advanced tools you need to prove a limit's existence. What this means is you're not lost in that maze of infinite paths anymore. You have a strategy. You are the detective now. So for the next problem you face, the question is, which path will you choose to crack the case?